Alright, time for a few special quadratics. A lot of special quadratics in my opinion, but there's two that are quite important to know how to factorize. What we've got here is what we call a difference of two squares. Can you think, well, I might just say difference of squares. Can you think why it might be called the difference of squares? Well, mathematics has a lot of fancy words like product means multiplication. Difference is basically subtraction. So if I wanted to say difference of 10 and 5, I wanted the difference between those two numbers. You intuitively know that's 5, hopefully, but the actual operation would be subtraction. That would give you the difference. So this is the difference of x squared, or x times x, and 5 squared, 5 times 5. So how can we factorize that? Well, we could go back to what we learned in the previous lesson. X squared, well, there's no x's, so 0x minus 25, and we could go through it analytically like that. So they multiply to negative 25, but add to 0. Now it's the square part that really helps us out here. What multiplies to negative 25 but adds to 0? Have a think. Okay. X minus 5, x plus 5. Interesting. It's like we've got the square root of 25 with opposite signs in both those brackets. Let's have a look at something else to see if it works out to be the same. What about x squared minus 81? Well, they're going to have to cancel each other out when they add, because there's no x's. And we have x minus 9, x plus 9. Those are the only two numbers that multiply to 81 but add to nothing, because there's obviously no x. So that's how we can factorize special quadratics. X plus the root of that number in one bracket, x plus the root of that number, x minus the root of that number in the other bracket. So just opposite signs. Let's have a look at expanding and see how that looks when we expand. I've got quite a complicated one here. I've got 3x minus 2 in one bracket, multiplied by 3x plus 2 in another bracket. So 3x times 3x, 9x squared. 3x times 2, 6x. Negative 2 times 3x minus 6x. And negative 2 times 2 minus 4. You can see here that when we collect like terms, the positive 6x and negative 6x would cancel, and we are left with 9x squared minus 4. So 9x squared minus 4 is actually a difference of squares, because we've got 3x all squared and we've got 2 squared. So we've got the difference of 2 squares. You can see how that becomes our two brackets. 3x plus 2 and 3x minus 2. Easy as. Okay, I've got for you 8 difference of square questions. So if you want to pause the video, maybe make a note on that. You might want to now pause the video and give these 8 questions a go. So, question 1, x squared, take away 16. So we notice that it's the difference of 2 squares, and therefore it's easy to factorize. X plus 4, x minus 4. Question 2, x squared, take away 64. Well, that's just x plus 8 in one bracket times x minus 8 in another bracket. I usually go positive and negative, but it really doesn't matter what way around you do it. Question 3, x squared minus 36. Well, It should be easy. X plus 6, x minus 6. We notice it's in the difference of two squares form. Here's a good one. X squared minus 100, x plus 10 in one bracket, x minus 10 in the other. Question 5 can usually stump a few people. They forget that the square root of 1 is just 1. So this one, x squared minus 1, that's the difference of x squared and 1. We have x plus 1, x minus 1. Now we've got 3 more complicated ones for you to have a go at. We have, for question 6, 4x squared minus 1. Well, what are the two things that are being squared? First thing being squared is 2x. That's being squared to give 4x squared. And the other thing is 1 is being squared. So this is going to become 2x plus 1, 2x minus 1. Hopefully that makes sense. Now I've got a couple, they get progressively harder now. Or these last two aren't too bad actually. We have 9m squared minus 16. What has been squared to give 9m squared? 3m. And what's been squared to give 16? 4. Those are the difference of our two squares. Our brackets become 3m plus 4, 3m minus 4. Question 8. What's squaring to give 36p squared? Well, that's 6p all squared, so that's going to go in both our brackets. And what's squaring to give 25? That's 5 squared, so it's going in with opposite signs because they're obviously still cancelling each other out to give a void, I guess, in the middle of that quadratic. Okay, one more special type of quadratic. What happens when we expand something like x plus 4 squared? So just x plus 4 squared. So that whole bracket has been squared. What does that mean? It means that that's x plus 4 multiplied by itself. Okay, so when we expand this, we have x times x times 4, 4 times x, and 4 times 4. Not so bad. That gives us the quadratic x squared plus 8x plus 16. So what's special about this? Well, these are called perfect squares because they're not two different brackets anymore. They're not two different brackets, they're two brackets that are the same. So they're called perfect squares because if you were to represent them as a square, x plus 4 times x plus 4, then all those sides would be the same. So it's a perfect square. Anyway, how do we factorize a perfect square? Well, let's have a look at x squared plus, let's have a think. What do I want to use? X squared plus 6x plus 9. Well, factorizing this normally, multiplies to 9, adds to 6. X plus 3, x plus 3. But we want to write this as a perfect square because the brackets are the same. So x plus 3 all squared because it's a perfect square. You might be able to see that when you've got two lots of the square root of that number, so square root of 9 being 3, and you've got two lots of that, you could go straight to that squared bracket. But that comes with experience. Right, here is 8 questions for us to have a go at. Question 1, x squared plus 8x plus 16. Give these ones a go. Okay, so we're going to write this as double brackets. So it's obviously x plus 4 times x plus 4. But we want to write this as a single bracket squared because it's the same bracket repeated. So it's obviously x plus 4 multiplied by itself, or x plus 4 squared. You can kind of cheat a little bit because these are obviously all perfect squares. So x squared minus 10x plus 25 is x minus 5, x minus 5, or x minus 5 all squared. It's starting to get a little easier now. So it's obviously 7 plus 7 is 14, and 7 times 7 is 49. So we know that this is going to be x plus 7 all squared. Question 4, x squared minus 6x plus 9. Well, it's obviously two lots of negative 3 give the negative 6, and 3 squared gives 9. So this is obviously just x minus 3 all squared. Question 5, x squared plus 12x, x squared plus 2x plus 1. Well, that's just x plus 1 all squared. Question 6, x squared minus 20x plus 100. That is x minus 10 all squared. Question 7, x squared minus 30x plus 225. Well, 225 is pretty hard to take the square root of, but negative 30 isn't hard to halve, so that's going to be x minus 15 all squared. So 15 squared is 225. You could do a quick algorithm on the side if you want to check that. Last one, x squared plus 26x plus 169. Again, 169 is quite hard to get the square root of, but these are perfect squares, so we should recognize that we're going to have half of 26. So x plus 13 all squared. So there we have it. Those are two special cases of quadratic factorization.